10.9 Stokes theorem. This is nothing new. This is exactly extending Green's theorem that you just learned, okay? What was Green's theorem? The curl F dot product with K is the line integral, okay? So the curl of a surface in the surface is the line integral. If we draw that, you can express this way. So that's R, okay? And that's R, and that's C, right? The boundary. Okay? So it's pushing the region to boundary, right? But this is 2D, right? In XY plane. But Stokes' theorem extends it to 3D version of Green. Okay? The surface is placed 3D XYZ. And that's S in our notation. And that's C. That's C. The curve, okay? And the surface, the boundary is curve C. This is empty inside. Okay? This is only surface there. It's not filled. It's not solid. Right? You have to remember that. And since it's rotating that way, counterclockwise, the direction of the surface is this, right? That's n, the normal factor to the surface. Okay? And that's the relationship. So before, it was time k that makes 2D. And dot n of surface, that's really 3D. Okay? No matter what is 2D or 3D, they're all line integral. Okay? Of the boundary curve. And then that value equal to the line integral, right? When you move here, right? That boundary, and you take the vector field, right? On that, and you project it onto that line. This is a line integral. Exactly the line integral. Okay? Alright. 자, 여러분의 이해를 돕기 위해서, 지금 어느 정도 이해가 됐을 거야. 그거를 좀 더 간단한 케이스를 여러 경우를 통해서 한번 확인을 해보죠. 그러니까 프루프는 못하겠고, 지금 매스메리컬 프루프까지 할 수는 없고, 인투이션만 주는 거예요. 자, 여기서 봐요. 자, 이게 S고, 여러 가지 경우가 있는 거예요. S가 이렇게 흘러가고, 자, 바운더리, 아니, C. 자, C가 이렇게 흘러가고, 그쵸? 이게 우리의 면이에요, S예요. 자, 여기에는 컬이 없어요. 왜? 벡터 필드가 한 방향으로 똑같이 균일하게 흘러가고 있어요. 그쵸? 그러면 여기다가, 바람개비를 놔도 안 돌겠죠. 그쵸? 컬이, no 컬이에요. 자, 그렇다면, 라인 인티그럴 한번 계산을 해봅시다. 대충. 자, 이렇게 되면은 내가 가는 방향하고 같이 있으니까 뭐예요? 플러스 넘버가 나오겠죠, 뭔가. 그치? 이거는 내가 가는 방향 90도니까 0이겠죠. 이쪽 면에서는 전부 다. 이쪽 면에서는 반대 방향이죠. 나는 이쪽으로 가는데 뒤로 가고 있지. 그럼 마이너스가 될 거 아니에요. 그쵸? 라인 인티그럴을 하면 이쪽은 또 0이고. 그러면 뭐가 돼요? 이게 균일하다면 0이 되죠. 라인 인티그럴이. 그쵸? 자, 컬이 0인데 라인 인티그럴은 0이에요. 오케이? 자, 그러면 컬이 없으면 라인 인티그럴도 0이다. 그쵸? 컬이 0이면 라인 인티그럴도 0이다. 그건 이제 이해가 됐죠. 그쵸? 이 관계를 보는 거야, 지금. 자, 다음은 이렇게 흘러가고 이렇게 흘러가고 이렇게 흘러가는데 C가. 근데 원래 벡터 필드가 위에 거는 다 왼쪽으로 가고 있고 오른쪽으로 가고 있어요. 그럼 어떻게 되겠어? 컬이 뭔가가 있는 거죠. 돌리니까. 여기다 만약에 바람개비를 놓으면 이 사이에다가 돌겠죠. 바람개비가. 그렇죠? 위는 이쪽으로 때리고 밑은 이쪽으로 때리니까 돌겠죠. 컬이 몇인지는 모르겠지만 있다라는 얘기예요. 자, 그럼 라인 인티그럴을 한번 생각해 봅시다. 같은 방향 플러스 이쪽 0 이쪽 플러스 이쪽 0. 그죠? 라인 인티그럴이 some number, positive number, 그렇죠? 오케이. 자, 이거는 똑같이. 그러면 컬이 이건 엄청 컬이 많죠, 그렇죠? 예, 플로우 자체가 그냥 도는 플로우예요. 그럴 수 있지, 그렇지? 예. 그럴 때는 이거는 플러스 컬이 굉장히 많다. 예. 자, 그럼 라인 인티그럴을 구해보면 여기 뭐야? 플러스, 여기도 플러스, 여기도 플러스, 여기도 플러스죠, 그렇죠? 다 내 진행 방향하고 똑같으니까. 그러니까 결국은 라인 인티그럴은 더 플러스가 되는 거죠. 그렇지? 결국 관계가 있다는 얘기죠. 정확한 수학적인 증명은 아닌데 이거를 빗대어서 얘기를 할 수가 있는 거죠. 오케이? 뭐 나머지들은 뭐 여기 이렇게 부분적으로 스몰 컬이 있을 때의 전체적인 값. 예, 여기는 위로 가고 할 때 뭐 서로 컬들 캔슬돼서 결국은 0이 되는 것들은 여러분이 한번 생각해 보세요. This is cylinder. I mean, not cylinder. This is kind of slanted, way. So it's like, 1 is a circle, but this is slanted on YZ axis. So if I draw that, that has to be, I guess it's hard to draw, but let's try to draw it. Okay? So that's S. Okay, this area, and that's C, the curve C. Okay, so that's the surface, and we have a lot of vector fields around it. That's what it is, and we're gonna calculate the work. This is work, okay, mechanical work, and so this is. So we determine. I mean, we think that this is hard to evaluate on a line integral, right? Because this path is a little bit tricky. We feel like, right? This slanted path is hard to evaluate, so we determined to use Stokes' theorem to evaluate that in double integral. Okay? And then since surface is slanted, we better parameterize it, right? It's not easy to, evaluate it. So we parameterize our surface. We're gonna parameterize this to be UV. Okay? And that parameterization, we do this. X is phi cosine u, as we do cylindrical. Phi sine u. C is 2 minus y, which is 2 minus phi sine u. Okay? And then our position vector for the surface is phi cosine u I plus phi sine u j plus 2 minus phi sine u k. Okay? And and now what? We have to, we can get this, right? Curl. We can get this. And we need to identify that surface, right? This is like the direction vector for the surface. Okay? This is a vector. It's a direction vector. You could write this way too. Okay? It's a direction vector of that surface. Okay, we can express that way. But anyway, yeah. Let's identify what this will be, this vector. This is what? You remember? Okay? And the reason that, it's VU, not UV, is this. That's R on XY plane, right? Meaning from here, that's R, right? That's R, this way, and R is getting increased, and this is theta, right? So this vector is V. R is V, according to our notation. And this is theta to be U, right? So it's a parallelogram between two two vectors, that's cross product, and that's our n. Okay? All right? That's our direction of the surface. You should be able to understand that, right? To calculate it. So anyway, that's I, j, k, cosine u, sine u, minus sine u, right? Ru is, with respect to u and v. That's minus v sine u, v cosine u, minus v cosine u. You should be careful about the direction, okay? Which one is first for the cross product? That should be meaningful for the right-hand side rule, okay? And physical meaning, all right? This one, if you calculate it, that, and, eventually, that's, the v is here 1, right? V is 1 in this case, so it's j plus k. So 1, 1. Okay. All right? And then, you have to get curl f now, which is I, j, k, d over dx, d over dy, d over dz, c, x, y, that's the field, right? So if you calculate that, that's I, j plus k, okay? And we are ready to get the w. F dot dr is integrating over r, which is I plus j plus k dot product with j plus k. That's the direction vector for the surface. Okay? And that's r2 dx dy, and that's 2 pi, right? Dx dy, it's a circle projected onto the xy plane. And that's pi r square, r is 1, so it's a pi. Okay? This circle. It's kind of projecting down to xy surface because the line integral, okay?